start the fourth lecture of the third week, and in this lecture I will be talking once again about fractional coordinates, and I will also talk about a way to draw structures on a plane, that is a planar visualization. So week 3 lecture 4 will be on fractional coordinates and planar visualization. And I will take the example of a diamond lattice. Now I have used the term diamond lattice, but it is not truly a lattice, it is not truly a Bravais lattice. So it is not a Bravais lattice, but what I mean by diamond lattice is that it is every atom is identical. So it's you can think of you can also think of it as an FCC with a two atom basis. So so one atom is shown in blue, the other atom is shown in green, and so an FCC with a 2 atom basis will have 8 atoms per unit cell, and that would be a diamond lattice. This is the structure for silicon or carbon, the diamond structure of carbon. Okay. It is not a Bravais lattice, and you can also think of this as in terms of something that we will see a little later. These are called the tetrahedral voids. So if you have an FCC lattice and you have half of the tetrahedral voids occupied, okay, then you will get an diamond lattice. Okay. So we will look at this, and we will see how to we will look at both the fractional coordinates and the planar visualization with this. Okay. So now let us look at the fractional coordinates. Now I have shown these two atoms in different color, the blue and the green. Okay, that is only for ease of visualization. Okay, in a diamond lattice, these two are the same atom. Okay, so how does this look? Okay, in terms of fractional coordinates, let's write the fractional coordinates of some atoms. So so if you recall, in fractional coordinates, you write it in terms of fractions of the cell sides of the cell. So if this is A, okay, then this coordinate, okay, so this let me label a few atoms. So let me call this 1, okay, I will call this atom 2, I will call this corner atom as 3. I will label only a few of the atoms. I will label this face center atom as 4. This is at the bottom face. Okay, I label this face center atom as 5. Okay, this is on the left face of the crystal, and this face center atom on the front face I will label as 6, and the tetrahedral, the green atoms, okay, I will label as 7, 8, 9 and 10. Okay, and I have just chosen a few of these atoms to depict. Okay, so what is the fractional coordinate of 1? Okay, and you can easily see that this is at the origin. Okay, so its fractional coordinates are 0, 0, 0. What are the fractional coordinates of 2? Now 2 is located a distance a away. Okay, so it is located a distance of the lattice parameter, and lattice parameter, if we call it a, okay, then the coordinates are a 0 0, but in fractional coordinates it is written as 1 0 0. Okay, and I'll write the actual coordinates here, and we will write the fractional coordinates here. Okay, so the actual coordinates for 0 0 0 are also 0 0 0. For atom 2, they are a 0 0, which in fractional coordinates becomes 1 0 0. Okay, what about atom 3? Okay, Now this is along the body diagonal. So you go along the body diagonal of the cube and you go to the other end. Let me I have been assuming that your coordinate system looks like this. So this is the x direction, y direction, and the z direction. Okay, so I've been assuming that this is a coordinate system, but I'll just state it explicitly. Okay. Now what about atom 3? And you can see again it's not too much work to see that this is nothing but 1 1 1, or in terms of the actual coordinates it is a 0 0. So these three were fairly easy. Okay. Now let's go to atom 4. Now atom 4 is located at the center of the bottom face, and here if you let's look at its coordinates. Its coordinates are a by 2, and 0. So in fractional coordinates it will just be half, 0. Okay. Now so it's halfway along the x, and let me just make it absolutely clear. So if you look at the coordinate of this atom, okay, its coordinate along the x direction is a by 2, its projection on the x axis, this coordinate is a by 2, and similarly on the y axis its projection is also a by 2. So clearly the x and y coordinates are a by 2. Okay. What about atom 5? Now I don't need to tell you too much about this. This clearly it is its x coordinate is 0 because it is on this face, on the side face. Okay. So the x coordinate is 0, so its fractional x coordinate will also be 0. The y coordinate is half, it's a by 2, so its fractional y coordinate will be, oh I should, this is a mistake, this should be 0, half, z coordinate is half, and I won't bother writing the actual coordinates. Okay, I won't bother writing these actual coordinates. And now what about atom 6? Now this has an x coordinate of half, has a y coordinate of 0, so it is in the xz plane, and it has a z coordinate of half in terms of fractional coordinates. If you want to write, you can write it as a by 2, 0, a by 2 in the real coordinates, in the non-fractional coordinates or the actual coordinates. Now things will get more interesting. Let's go to atom 7. Now atom 7 is along the body diagonal, okay, and it is 1/4 the way along the body diagonal. So it is a quarter of the way along the body diagonal, and this, if you make a projection, and let me show it in a different color, let me show it in this orange color. So if you project it along each of the axes, okay, you can easily see, okay, that its coordinate is actually a by 4, a by 4, a by 4. Okay, so it has, so none of the coordinates are 0. Each of the coordinates is quarter of the lattice parameter. Okay, so this distance, okay, so this is making a distance of a by 4. Okay, now this gives me the fractional coordinates of 1 by 4, okay. Now remember, point 3 is 1 1 1, okay, and this is 1/4 1/4 1/4. So clearly it is 1/4 of the way from the origin, which is point 1, to point 3. Okay, so this is the fractional coordinate of point number 7. What about point number 8? Now point number 8, it's along this body diagonal. So it is along a different body diagonal. Let me show that body diagonal. So point 8 is actually located along this body diagonal. and so its coordinate is going to be, so its x coordinate is a is 3a by 4, the y coordinate is also 3a by 4, and the z coordinate is a by 4. Okay, so it is at the same height as atom 7, okay, but it is shifted in the x and y directions. Okay, and you can easily see now the fractional coordinate is 3 by 4, 3 by 4, 1 by 4. Okay, now you can go to atom 9. Okay, now atom 9 is actually along a body diagonal that starts at this atom, okay, and ends up at the atom that is diagonally opposite, that is this atom. So this is the body diagonal, goes through this and comes here. Okay, now the coordinate of this atom, okay, now you can easily, I'll just write the fractional coordinates. You can easily see now this is closer to the top face. Okay, so its z coordinate is actually 3 by 4. Okay, its x coordinate is also 3 by 4, but its y coordinate is 1 by 4. Okay, and you can see this that this is close to the front face, close to the yz, close to the xz face. Okay, close to this xz plane. Okay, it is only 1/4 of a distance from the xz plane, so it is y coordinate is 1/4, but it is 3/4 the lattice parameter distance from the xz plane, from the xy plane, okay, and from the yz plane. Okay, and finally, let's you can again see atom number 10. Okay, so this now atom number 10 is actually closer to the yz plane. So its x coordinate is 1 by 4, y coordinate is 3 by 4. Okay, so it is closer to the back face of the cube, and its z coordinate is also 3 by 4. Okay, so these are the fractional coordinates of the atoms in the diamond lattice. You can easily label all the other atoms. Okay, I won't bother doing that. Okay, but now what we see is that drawing this diamond lattice as a cube, okay, makes it fairly difficult to label all the points. Okay, so what is done very commonly is to use something that is called a planar representation, and these fractional coordinates are actually put in the planar representation. So let's take a look at that. So here we want to show a planar representation. Okay, you can let's say we start with we will just keep in mind that this is the bottom plane has a z coordinate of 0, top plane has a z coordinate of 1. Okay, the plane containing this atom has z equal to 3 by 4, and this atom, the face center atoms, have z equal to half, and these green atoms have z equal to 1 by 4. Okay, and I am not, this also has 1 by 4. This has z equal to 3 by 4. Okay, there are several other atoms. This also has z equal to half. I'm not showing all the atoms that have, there will be this atom and the atom in the back face that also have z equal to half. Okay, now so the way to show the fractional coordinates is let's take the xy plane, and we'll just take it for convenience. You can take any plane you want. Okay, so now first what is done is you start with the z equal to 0 plane. So, in the z equal to 0 plane, you have these 5 atoms. Okay, I will just consider one unit. I will just consider this conventional unit cell. So, so let me again label the atoms 1. I will take 2. Okay, 3, 4. Slightly different labeling I am using 1, 2, 3, 4, 5. Okay, just to make it absolutely clear what we are talking about. Okay, and again this is the x axis, and this is our y axis, this is our z axis, and your origin is located at 1. So now you draw it in the xy plane. So at the origin you have an atom, this is your atom 1, and then you have at x equal to 1, y equal to 0, then you have x equal to 1, y equal to 1, and x equal to 0, y equal to 1. So this is the x, this is atom 1, this is atom 2, this is atom 3, this is atom 4. Okay. Atom 5 is located at the phase center, and I am drawing it here. Okay. This is atom 5. Okay. So all these are located at z equal to 0. Okay. So in the planar representation you do not explicitly write z equal to 0, and but I'll just write this here. I'll write in brackets. Okay, just z equal to 0. Now what we do is we go up, we go to the next value of z where you have atoms, and here we see that z equal to 1 by 4th. There is this atom. There are the 2 of the green atoms at z equal to 1/4. Okay, and if you go back and see their fractional coordinates. Okay, I am here now I am referring to these 2 atoms. I'll just shade them, this atom and this atom. Okay, and if you go back to their fractional coordinates, okay, the fractional coordinate of this is x equal to 1 by 4, y equal to 1 by 4, and z equal to 1 by 4. Okay, so what is done is you show the z equal to 1 by 4. Okay, so I'll use the blue color for z equal to 1 by 4, and now I have this atom at x equal to 1 by 4, y equal to 1 by 4. So if 2 is at x equal to 1 and 5 is at x equal to half, okay, clearly this is at x equal to 1/4. And similarly the other atom at z equal to 1/4 is located at x equal to 3 by 4, for y equal to 3 by 4. So again let me label these atoms. Okay, so let me call this atom number 6 and atom number 7. Okay, then this is atom number 6 and atom number 7, and this blue color atoms are located at z equal to 1 by 4. Now so you can see in this one representation I have shown the 4 atoms located in the z equal to 0 plane and the 2 atoms located at z equal to 1 by 4 plane. Next you go to the z equal to half. Now z equal to half. Okay, so now let me look at this atom number 8. This is located at z equal to half. Now the coordinate of atom number 8, okay, will tell you that this atom is located at x equal to half, y equal to 0, z equal to half. So x equal to half and y equal to 0. Z equal to half I will show by this different color. So I will use this the light blue color for z equal to half. Okay. Now is this the only atom at z equal to half? No, you have this atom also at z equal to half, and you have these 2 atoms also at z equal to half, and you can easily see that their coordinates are this, and this. Okay, so you have if you take this atom, this has z equal to half, x equal to 1, okay, and y equal to half. So x equal to 1 and y equal to half. Similarly, the atom on the back face will have y equal to 1, x equal to half, and z equal to half. This atom out here will have x equal to 0. Okay, so it is in the yz plane. This atom has x equal to 0 and z equal to half, x equal to 0. Okay, so this represents, so now what we have done is we have shown 3 planes. Okay, already we have shown 3 planes. Now there is one more plane, z equal to 3/4, and let me use the green color for z equal to 3/4, and again you can see by very simple that this has 2 atoms at z equal to 3/4. One is located here, one is located here. So this is z equal to 3/4. Okay. Now so this is a planar representation of the entire diamond lattice. Okay, and we can see that it's quite nice because you show all the atoms in one plane. Okay. Now the next layer of atoms will be at z equal to 1. Okay. Now z equal to 1 should be identical to z equal to 0 because of the translational symmetry of the crystal. So the z equal to 1 plane, that is, you will have exactly these 5 atoms which are the same 5 atoms that you had at z equal to 0. Okay, so we don't show from z equal to 1 onwards. Okay, and typically the way this is shown is not with different colors. Okay, you can use just one color, but you show what is the coordinate. So I'll just show how it is shown typically. So this diamond lattice will be shown in this manner. So you have a square, and usually if you don't label some value of z, it means it is z equal to 0 or z equal to 1. So z equal to 0 and z equal to 1 are identical and they are not labeled. Okay, then you have these two, and here you just write 1/4. Okay, then you have these 4. Write it a little more legible. Let me just show. Just for convenience, I'll use a slightly more legible notation. Okay, so let me just show them as points, small points. Okay, then it will be a little more legible. Now this point is at 1/4. This point is also at 1/4. Okay, then you have these 4 points at half, 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 and half, and you have these 2 points located at 3/4. Okay, so this is the planar representation of the diamond lattice, and there is a small point about this, that you could have swapped these z equal to 1/4 and z equal to 3/4. Okay, you could have swapped them and you would have gotten an exactly equivalent lattice. Okay, it doesn't look identical. Okay, it doesn't look identical. Okay, but at least in this view it doesn't look identical, but you would have got an equivalent lattice. You would have still got a diamond lattice. So you could have had a diamond lattice. You can imagine that you just invert about this point. Okay, then you would have got you would have seen that that the 2 green atoms would have been 2 green dots here would have corresponded to z equal to 1 by 4th, and these could have corresponded to z equal to 3 by 4. Okay, so the diamond lattice is actually not a Bravais lattice. Okay, this shows that it is not a Bravais lattice, and but it is still a very commonly used term. So I'll use the term diamond lattice, but you should always keep in mind that it's not a Bravais lattice. So the planar representations are something that you will find in several books. You will find it in several internet sites, and they are regularly used. And always they are represented in terms of fractional coordinates. You can extend these to more to unit cells of any shape. Okay, and these are regularly done. Okay, so people often use fractional coordinates and this planar representation. It makes it much easier to show it on a flat piece of paper. Otherwise, you would require 3D models to visualize things. Okay, and what we'll see is that the symmetries are also very nicely seen in this planar representation. So you can show certain symmetries nicely in this planar representation. So I will conclude this lecture here for now, and in the next class we will summarize what we learnt in week 3, and we will also we'll take an example of identifying all the symmetry elements of the diamond lattice. Thank you.